hello friends, now we will continue with some theorem based on Riemann integral. Okay, Riemann integral functions. So the theorem is the criteria for function to be Riemann integral. Okay, till we know only one criteria to prove a function is Riemann integral. What is that? That criteria was lower integral of the function corresponding to partition P is equal to upper integral of that function corresponding to same partition P. If these two are equal, then function is still Riemann integral. Okay. Now we will see two criteria for function to be Riemann integral. Okay. Out of which first form of integrability condition. These are the two conditions. If this satisfied, we say that this function is Riemann integral. Okay. So first criteria is, let we have given a function f which is bounded on this closed and boundary interval AB. Okay, and function is integrable on AB. If only for any epsilon greater than 0, we can find delta such that for every partition P with norm of the partition less than delta, if difference between upper sum and lower sum is less than epsilon. Okay, so what this criteria implies, a function is Riemann is integrable, means Riemann integral if only this is satisfied, that upper sum minus lower sum for the partition P with norm of partition less than delta is less than epsilon. If we can find such a delta for any epsilon greater than 0 satisfying this condition, then function is Riemann integral. This is the first form of integrability condition. So we will prove first, this is if and only statement, so we have to prove this in both methods. So we will first prove assume first part and then we will prove. Here we will assume first, suppose function is Riemann integral, and we will prove this condition is okay, and then we later on we assume this condition is satisfied, then we will prove function is Riemann integral. That is first sufficient part or then necessary part or vice versa. Okay. So we will assume first function is Riemann integral. Okay. So let our function f is Riemann integrable. Okay. Now we will know only one condition till which implies function is Riemann integrable. What is that? Upper integral is equal to lower integral. Okay. So this implies upper integral of the function is equal to the lower integral is equal to upper integral of the function. Since function is Riemann integrable, lower integral is equal to upper integral is equal to some common value, that is the, and this common value we can note as integral a to b f of x dx. So f dx. Okay, this is the common value of upper and lower integral, which is nothing but the integration of that function. Okay, since function is Riemann integral, we can write this. Okay, now we know one inequality. What is the inequality? That lower sum is less equal lower integral, which is less equal upper integral, is equal upper sum. Okay, but there is one theorem known as Saurabh theorem, which says if we have a function and which is bounded on interval a to b, and there is some partition P such that norm of the partition less than delta. Okay, the Gaikwad theorem says that we can add some number or element to the upper integral so that it becomes greater than upper sum, and we can subtract some element from this lower integral so that it becomes less than lower sum. Okay, so that is the Gaikwad theorem. So by Gaikwad theorem, for any epsilon greater than 0, for any epsilon greater than 0, there is a delta greater than 0 such that for any partition P with norm of partition less than delta, we have that this upper integral of function f, okay, plus some small arbitrary element epsilon by 2 is C. First up, we know upper integral is equal upper sum, but if we can add this arbitrary small element such that when we add this two element, this upper integral, this become greater than upper sum. And similarly, if we subtract from lower integral this arbitrary small element, this become less than lower sum. This is the Darboux theorem. Okay. So upper sum is less than this and lower sum is greater than this. Now we will take this difference UPF minus LPF. Okay. So UPF, upper sum for the function with partition P minus lower sum for the function with partition P. Okay. Now UPS is less than, okay, and LPF is greater than, but we have to maintain same sign here, and we want here minus of LPF. So what we do? Just multiply both sides by minus sign. So if we multiply by minus, this become minus, this become plus, the sign is changed and this become minus. Okay. So UPF is less than this and minus LPF is less than this. So we can write here less than. Since UPF also is less than, LPF also become less than. So subtraction also less than. So UPF is less than this number. So write here upper integral a to b f of x dx plus epsilon by 2 minus LPF. What is the minus LPF? Minus lower integral a to b f of x dx and plus epsilon by 2. Okay. Now since function is Riemann integral, we already seen lower integral is equal to upper integral is equal to integral of f. So this upper integral and lower integral are same. This is plus, this is minus. So this get cancelled. Okay. So what remain only epsilon by 2 plus epsilon by 2. It is only epsilon. Which implies upper sum minus lower sum less than epsilon. Okay. So we have proved this. Now in next part we will assume this and prove function is Riemann integral. Okay. Now we will assume that there is a for any epsilon greater than 0, there is delta greater than 0, such that a difference between upper sum and lower sum is less than epsilon. Okay. Whenever norm of partition is less than delta. Now we have to prove that function is Riemann integrable. That is upper integral is equal to lower integral. This is the next half part of this proof of this theorem. Okay. So we have given this. We know our standard inequality, that is lower sum is always less equal lower integral, which is less equal upper integral, and upper integral is always less equal upper sum. Okay. Now from this we can write that this upper integral of the function less equal upper sum. Okay. Also from here we can write that this lower integral of the function is greater equal, okay, is greater equal or lower sum. Okay. if you multiply this both sides by minus, then what happens? Then we can write that this lower integral minus n, lower integral a to b of the function. Since we are multiplying by minus, first this was smaller part becomes greater. So this becomes okay. This minus of lower integral of the function become less equal minus of lower sum. Okay, from this lower integral was greater equal lower sum, but we are multiplying by minus. So lower sum minus of lower sum become greater equal minus of lower integral. Minus of lower sum become less equal minus of minus of lower integral become less equal minus of lower sum. Okay. Now since upper integral are greater equal lower integral, the difference between upper integral and lower integral must be greater equal 0. So difference must be greater equal 0. Difference between upper integral and lower integral. So upper integral a to b of the function minus lower integral of the function. Since upper integral is always greater equal lower integral, difference between upper integral and lower integral must be greater equal 0. And see, upper integral is less equal up of, so this is less equal upper sum, and minus of lower integral is less equal minus of lower sum. So again lower is less equal minus of lower sum. But see, this is still less than epsilon. So put this value here. So we have 0 less equal lower integral of the function, sorry, upper integral of the function minus lower integral of the function. This is less equal this, and this part is less than epsilon. This is less than epsilon. Now epsilon is any arbitrary element, so we can take epsilon very close to 0. So letting epsilon tends to 0, what happens? The difference is greater equal 0, less equal 0. So only one option remains, that difference must be equal to 0. This implies the difference must be equal to 0. Why? Because there is some element which is greater equal 0 and also less equal 0, because we have to take epsilon into 0. So with the term which is greater equal 0, less equal 0, so only one option, that this term must be equal to 0. So difference between upper integral of the function and lower integral of the function must be equal to 0. That is, this is equal to this. That is, upper integral of the function is equal to the lower integral of the function, and this means function is Riemann integrable. Okay, function is Riemann integrable on the interval R, which is the closest boundary interval T to B. So this is the first form of integrability condition. On a similar line, we can prove the second form of integrability condition. We will see statement of that second form of integrability condition, which is very much similar to this first form. Okay, only very small difference is there. There is no need to put the condition like norm of the partition is less than delta. Okay, so I left the proof of second form to you. So we will just see what second form of integrability condition says. Okay, this condition is nothing but very similar to the first form of Riemann integrability condition. Okay, so if a bounded function here is defined on AB, then it is Riemann integrable on the interval AB if only for every epsilon greater than 0 we can have partition P such that difference between upper sum and lower sum is less than epsilon. Okay, so we have reduced some extra condition from first form of integrability condition. Here we don't need that the norm of partition is less than delta, or we can find delta or not. Okay? This is the statement for second form of integrability condition. Okay? Now we will see some corollaries based on these two integrability conditions. Okay, so corollary one is we have to know that every continuous function is integrable or Riemann integrable. Okay, so let f be the function which is continuous on this closed boundary interval AB. Now, if this set is closed and bounded, it is compact, and we know the one property from linear analysis that if function is continuous on compact set, then it is uniformly continuous. Since this is compact set, f is uniformly continuous on this closed and boundary interval AB. So by definition of uniform continuous function, we can write for any epsilon get ranges. Okay, so if we take any positive number or say epsilon, or we can say epsilon upon b minus a. Since epsilon is positive, this a to b is closed boundary interval and b is greater than a, so b minus a is a positive. So for any positive number, so for any epsilon upon b minus a greater than 0, there exists a delta positive, delta greater than 0, such that whenever the two elements x1 and x2 belongs to this interval, such that x1 and x2 belongs to this closed boundary interval AB and satisfy difference between x1 and x2 less than delta, we must have difference between value of function at x1 and x2 less than that positive number. The difference between f of x1 and f of x2 less than that positive number epsilon upon b minus. This is nothing but the definition for uniformly continuous function, which says you take any two elements of the interval. If difference between that two elements is less than delta, the difference between the value of function at x1 and x2 is also less than that positive number epsilon or epsilon upon b minus a. This is the definition of uniformly continuous function. Okay, uniformly continuous function generally means if there are 2 points, if their difference is less than some value, so delta, difference between the value of function at the 2 point also less than some positive number. Okay, so difference is small. If difference between 2 points is small, difference between value of function also very small. So the value of function, difference between value of function does not go very high. Okay, so this is the uniformly continuous function. Okay, so we know. So we will take some partition. Okay, so let P is equal to the partition starting with first point A. Say x0 is equal to A, then x1, then x2 up to xn is equal to B. We have taken some this partition P. And capital N K, we know it is nothing but the supremum of the function, and small n k is the infimum of the function, but when in kth subinterval, we due to this partition interval gets divided into subintervals. Okay, so whenever x belongs to xk minus 1 and xk, that is kth subintervals. Okay. Now we know difference between capital N K and small n k, that is supremum and infimum at kth interval is nothing but supremum of mod of f of x dash. Okay, where x and x dash belong to the kth subintervals. Okay, where x dash belongs to ik. Okay, kth subinterval. We know we are already through this identity, okay? This equality, that if supremum and infimum in the kth interval is nothing but supremum of difference between two value of function. Okay. Now, from put this value of it will take any two values. Difference between value of function is always less than epsilon upon b minus a. So difference between this must be also less than epsilon upon b minus a. This is less than supremum of epsilon upon b minus a. But epsilon upon b minus a is some constant number. Its supremum is epsilon upon b minus a. This implies supremum of the function in kth interval minus infimum of the function in kth interval is less than epsilon upon b minus. So now we have to finally show that function is Riemann integrable, and we will use condition of Riemann integrability. So for that purpose we have to find difference between upper sum and lower sum. So here we have to multiply by length of the subintervals. Here also length of subintervals, and we will take summation. So this becomes upper sum. Here we can write lower sum. Okay. So multiply by delta xk and take summation. Okay. This implies summation mk delta xk. Okay. Now I will directly separate the summation. Summation over this into delta xk, then summation over this into delta xk. Okay. So capital mk delta xk summation minus small m that is infimum into delta xk and summation varies over partition, that is k is equal to 1 to n is less than, multiply this by delta xk and take summation, but this is constant as okay, this has no rule in summation, so we can take it outside. So less than epsilon upon b minus a into summation delta xk, where k varies from 1 to n. Okay. So summation over k is equal to 1, k is equal to 1 to n, k is equal to 1 to n. What is this? Upper sum. Okay. This implies UPF. What is this? Lower sum. Summation small m k delta xk. Okay. Is less than epsilon upon b minus a as it is. Now sum of length of all intervals. Okay. It's nothing but sum of total interval. So length of total interval. See, IKs are the subintervals of this interval. So sum of length of each subintervals is nothing but length of the whole interval. Length of this interval is b minus a. The value of this sum is b minus a. Okay. B minus a. So this gets cancelled. So UP upper sum minus lower sum implies upper sum minus lower sum is less than epsilon. So why is it? By first form of integrability condition. This applies the function which is continuous always Riemann integrable or integrable. This is the first corollary. So now we will see a second corollary based on that two integrability conditions. Okay. So the second corollary is if function is monotonic in the closed boundary interval AB, then it is also integrable in that interval. Okay. So first corollary was every continuous functions on closed boundary interval is Riemann integrable, and second is every monotonic functions is Riemann integrable in that closed bounded interval AB. Okay. Now we will prove this corollary. So suppose function is, let f be the function, let f be the function which is monotonic on AB. So what is monotonic function? Monotonic functions are two types, either monotonic increasing or monotonic decreasing. Monotonic increasing function means if we add, so there are two values x1 and x2. if x2 is greater than x1, the value of function at x2 also greater than value of function at x1. That is, if you increase value of x, value of f of x also goes on increasing. So graph like increasing graph of that function. It is called moderate increasing. Okay. So like if x1 is less than x2, then value of function at x1 is also less than value of function at x2. That is, if x2 is greater than x1, value of function at x2 is also greater than x1. So f of x2 is greater than f of x1. Whenever x2 is greater than x1, the function is said to be moderate increasing. That is, if you increase the value of x, value of a function at that point x also increases. It is moderate increasing, and other moderate decreasing, which like just reverse of this. Okay, which says if x1 is less than x2, then f of x1 is greater than f of x2. That is okay. Which says if you increase the value of x, value of function decreases, which is moderate decreasing function. So let every function is monotonic on A. Now we will assume any one of these two types of this monotonic function. So let us assume the function is monotonic increasing. Okay. So let every function is monotonic on this interval A to B. Okay. Since function is monotonic, so its bounds, it has two bounds up. One is f of b, other is f of a. So why? Because other function is increasing or decreasing. If function is increasing, then since b is highest value of this interval, function has maximum value at point b and minimum value at point a. If function is more than decreasing, the function has maximum value at this lower point f of a and minimum value at this upper point f of b. Okay. So we will assume our function is more than increasing. Okay. Now T is the partition of this interval. Okay. So the first point is A, which is x0, then x1, x2, then last point, which is B. We can say this xl. Okay. So this is the partition, and we choose a partition such that norm of partition is less than epsilon upon f of b minus f of a plus 1. Okay. So we have chosen a partition such that norm of the partition is less than this element. Okay. So let function is monotonic increasing. Okay. Now we have to prove that function is Riemann integrable using our integrating condition. So what is the condition? Then we have to prove difference between upper sum and lower sum is less than epsilon. Okay. So we have to find upper sum, difference between upper sum and lower sum. Okay. Now we know mk, that is supremum of the function in kth interval. Okay. So we will assume our function is monotonic increasing. Okay. So let it be the monotonic increasing function. Okay. So mk is supremum of f of x and small mk is equal to infimum of f of x, where x belongs to kth subintervals. Okay, where x belongs to xk minus 1 and this is the kth subinterval. But see, since function is monotonic increasing in this interval, xk is maximum value, so function has maximum value at point xk and minimum value, that is small mk infimum at small value xk minus 1. Okay. See, our function is monotonic increasing. So if we put highest maximum value, function get again, we will see maximum value of the function. See, xk is highest value in the interval. So supremum of the function must be f of xk, and xk minus 1 is the minimum value of the interval. So infimum of function is nothing but f of xk minus 1. Okay. So this is equal to supremum of the function is lies at point xk. We get at point xk supremum of function, because xk is maximum and function is monotonic increasing, so maximum value occurs at this point. So supremum of x is nothing but f of xk. Okay, and xk minus 1 is the minimum value of the interval. So minimum value of the function occurs at this point xk minus 1. So small mk is equal to f of xk minus 1. Okay, this is our small mk. So we have get capital mk and small mk. Capital mk is f of xk and minimum value is f of xk minus 1 for each interval. Okay, so now we will take difference between upper sum and lower sum. Okay. So upper sum minus lower sum is nothing but difference between capital MK delta xk minus difference between sum of small mk delta xk. Okay, so minus form k is equal to 1 to n, k is equal to 1 to n. Now here is summation, here is summation, k is equal to 1 to n, k is equal to 1 to n, delta xk. So take this common. So this is nothing but the difference equal to this difference between the summation k is equal to 1 to n. What is common? Summation is common. Delta x is common. So write whatever remaining. So remaining is capital MK minus small mk into delta xk. Delta xk is nothing but the length of kth interval, and norm of p is nothing but the length of maximum length of the interval. So norm of partition nothing but the maximum length of the intervals. So maximum length always less equal greater equal any other length. Since it is norm, what is the definition of norm of partition? Norm of partition is the length of highest length of the any subintervals. So any other length of the interval is always less equal to that norm. Okay, since norm is always greater equal to any other length, because norm in itself a highest length of any interval. Okay, so this we replace delta xk by norm. So we have to replace this equal to by less equal, because this norm is always greater equal. So this delta x is less equal norm of p. So this becomes, this is less equal summation k is equal to 1 to m capital mk, and what is the value of capital mk? F of xk. So f of xk. What is the value of small? Okay, we will write this. What is the value of small mk? It is infimum function occurs at left end point, that is f of xk minus 1. F of xk minus 1. Okay. And this is less equal this norm. Okay, that is norm of the partition, that is v of. So now again this part, this here norm of p here, and we have taken norm of p less than this value. So put this value here. So this less equal become now strictly less than. Norm of p is less than epsilon upon f of b minus f of a plus 1, and this summation rise from k is equal to 1 to n. Okay, so we will take this summation now. Okay, so first put k is equal to 1, we will get f of 1, f of x1 minus f of 0. So f of x1 minus f of x0. Then put x is equal to, we will get f of x2. So summation, so plus f of x2. Put k is equal to here. Put k is equal to here. 2 minus 1, 1. F of x1. Okay. Plus continue up to so on. At last put k is equal to m. We will get f of xn minus f of xn minus 1. So see, by observation. Okay. Each term. So see here, f of x1 was in plus, f of x1 is not minus. They get the answer. Here is f of x2 in plus. In next term, we will get f of x2 in minus. We will get cancel. Finally, This f of xn minus 1 is in minus. Before this term, f of xn minus 1 will be plus. So only two terms remain. This last f of xn and this minus f of x naught. Okay. So this is less than epsilon upon f of b minus f of a plus 1. What remain only? F of xn, f of xn minus f of x naught. Okay. What is xn? Xn is nothing but our b. So instead of f of xn, we can write f of b here. So f of b. What is x naught? X naught is nothing but our a. So we can write f of a. Okay. So in numerator f of b minus f of a, in denominator f of b minus f of a plus 1. So this upon this value is less than 1. Why? Because here is something, this f of b minus f of a. Okay. Here is also f of b minus f of a. But here extra 1 is added. So anyway, this upon this is less than 1 into epsilon become less than epsilon. See. Suppose this value is 1. Okay. So in the numerator there is 1 upon this value is 1. Okay. 1 1. So plus 1 plus 1 which is 2. 1 by 2 into epsilon. So half epsilon which is less than epsilon like this. This values are same. But extra 1 is added. So this numerator and denominator become less than 1. So 1 into epsilon, so less than epsilon. So we are sure that difference between upper sum and lower sum less than epsilon. This is upper sum minus lower sum less than epsilon. So by the condition of integrability, every modelic function on the boundary interval AB is always integrable. We will see one very easy example. Example is that the function is continuous and non-negative on AB. That is, function is always greater or equal 0. Takes positive value only. Greater or equal 0 on closed boundary interval AB. Then show that the integration of the function is always also greater or equal 0. So simplicity theorem means if function is non-negative, that is always greater or equal 0, then integral of the function also greater or equal 0. So function is non-negative, so always greater or equal 0. Okay. So and f is continuous. Okay. So f is continuous function. Okay. And you are just seeing a corollary that every continuous function on closed boundary interval is always Riemann integrable. This implies f is Riemann integrable on the interval AB. That means lower integral is equal to upper integral is equal to value of that integration. Okay. This means lower integral. Okay. Of the function is equal to upper integral is nothing but the integration of that function. Okay. Since function is continuous, it is integrable. Now, since function is greater or equal 0, and first we will take partition. Okay. Let P is equal to first point of the partition is x0, then x1 up to xn, nothing but this point be the partition of the interval AB. So now since function is always greater or equal 0 in whole interval AB, function is greater or equal 0 in each sub intervals. Okay. So minimum value and maximum value of the function are always greater or equal 0. Since function is greater or equal 0, its minimum value or maximum value must be greater or equal 0 because functions take only positive value. So minimum value and maximum value cannot be negative. This implies mk and that is minimum value and maximum value for the function f. Okay, or we can write mk which is just we take we don't need both values, though they are greater equal 0. We will use here only one value, that is smallest value. So we will take mk is equal to infimum of the function in case subinterval is also greater equal 0. Since function is always greater equal 0, whether it is minimum value or maximum value, it should be also greater equal 0. So we take minimum value and which must be greater equal 0, where x belongs to subinterval xk minus 1 xk case subinterval. Since function is greater equal 0 in the whole interval AB, function must be greater equal 0 in each subinterval. So minimum value or maximum value must be also greater equal 0 in each subinterval. So since mk is greater equal 0, we have lower sum LCF is equal to summation k is equal to 1 to n. This means infimum value small mk into delta xk. Now see, mk is always greater equal 0. Okay, delta xk is the neighbor length of the interval, and length cannot be negative, so length also greater equal 0. So both these values are greater equal 0. So therefore also greater equal 0, and this sum total sum must be also greater equal 0. So LPF is also greater equal 0. LPF is greater equal 0. Why? mk is already greater equal 0, and delta xk length, delta xk is length, which is always greater equal 0. Length cannot be negative, so lower sum always greater equal 0. So least upper bound, so LUB of LPF, since we take any partition for this function, lower sum always greater equal 0. So least upper bound of set of all lower sum is also greater equal 0. What is mean by least upper bound of set of lower sum? Nothing but lower integral. You know definition of lower integral is LUB of or least upper bound of lower sums, but least lower sum is greater equal 0. So least upper bound also greater equal 0. It cannot be negative. So this implies least upper bound of lower sums, nothing but the lower integrals. Lower integral of the function is always greater equal 0. But function is Riemann integral. So lower integral is equal to upper integral is the value of integration. This means we will write so since lower integral is equal to upper integral is equal to integral, and lower integral is greater equal 0. This means this integral is also greater equal 0. Integral of the function from a to b it must be greater equal 0, because lower integral is equal to upper integral is equal to integration of the function, and this is greater equal 0, so this must be greater equal 0. So if function is greater equal 0, it is continuous on the boundary interval AB, the Riemann integral also greater equal 0, or integration also greater equal 0. So using the same idea, I will give you homework is to prove if there are two functions f and g, both are Riemann integrable, okay, and f is less equal g, okay, then integration of f is also less equal integration of, okay, where f and g are Riemann integrable. Very easy, bro. Okay, you can do it. Okay.